Thank you very much. And thanks a lot for the invitation. And I'm very happy to be finally here. I'm going to report on some kind of long project together, initiated with Hao Wu, who's at Tsinghua, and a couple of students also who have been involved in parts of the project. Hope you can hear me fine. Yes. What else? This is me. You can find me in various email addresses. I think you know maybe the Bonn one already, but actually split in two places now, in Bonn and in Helsinki. So just to avoid confusion. Right, let's see. It does move. So here I copied kind of what I promised in the abstract, at least some keywords there. So I promised to talk about random cluster models at criticality with various boundary conditions. Let me say I'm always be in the plane, so everything is in 2 dimensions. Critical case. The problem of finding crossing probabilities, like Wendelin was kind of hinting at in his talk already. And one can cook up some conjectures of what these crossing probabilities should be. And one can show them in a bunch of example models, basically those which are somehow quite integrable, meaning that you can calculate the quantities explicitly and then check what happens in the scaling limit. Or when you have convergence of interfaces to SLE variants. So unfortunately for the random cluster models, to my knowledge, which may be outdated because of the pandemic, so please feel free to make remarks on some recent progress if I ignored some. We only know for the FK representation of the Ising model, the convergence of the interface. So that's somehow going to be the main focus, and maybe it's appropriate for the 102 years of the Ising model. And I'm going to mention here and there some kind of CFT connections. I didn't make slides about that, so please feel free to ask or point out if you have questions also in the middle of my talk, and I can explain more.
How does it depend on the lattices you consider?
So we've been considering mainly the square lattice, because somehow it's the easiest setup. What you need is most often convergence of the interface, so in whichever generality that has been proven. So for example, isoradial graphs for the FK-Ising should probably work. We're going to have some marked boundary points, and maybe we need some regularity near the boundary points, which probably also can be relaxed. So I've been mostly focusing in this project kind of finding, in the easiest setup, finding the CFT description and not really focusing on universality, but that's a great question. So it should not depend on the lattice. And we are having a bunch of experts here about universality, so I'm hoping also maybe they have some more comments along the way on which lattices, which things have been proven. Okay, so I think for this audience we don't need much motivation, so somehow motivation to look at these critical models and scaling limits is of course the connection on the one hand to CFT, and as a detour, as Wendelin was talking about CLE, I will be talking about SLE just a little bit, which has been a very powerful tool in verifying these conformal invariance properties. And as you may know, SLE should also be related to conformal field theory as representing some kind of boundary condition changing operators. So SLEs are caudal curves between 2 boundary points of some domain. So that's a difference to Wendelin's talk, where he was looking at loops inside the domain. Okay, so just a very brief recap of the random cluster model for those of you who need a reminder, or maybe there may be someone who hasn't seen it before. Not sure, maybe the notation anyway. So it was proposed by Fortune and Castellane as a unified model for percolation type phenomena. And a particular case of that model. So here on the right is the spin-Ising model simulation. I think it has Dobrushin boundary conditions. And that's dual, like Wendelin was mentioning, to a model of loops. It's a bit small here, but the picture will come bigger later, which is the FK-Ising model, which is a particular case of random cluster model. And then there's a plethora of these models with a parameter describing the cluster weight and the percolation probabilities. And so configurations will be living on some, let's say, finite graph. They're going to be denoted omega. They depend on edges of the graph. And edges are open or closed, so 0, 1. And the most familiar one, of course, is Bernoulli Bonn percolation, where you just flip maybe a p biased coin to decide if you're closed or open, according to probability p and 1 minus p. So that's an example of a random cluster model, the simplest one. So here is again, if you forget about this Q, you will have Bernoulli percolation, right? So probability of a configuration is proportional to something like that. And if you add this cluster interaction, parameter Q, you will get a more general random cluster model. And then you just weight each cluster by some positive parameter. And as was already mentioned, properties of the clusters. So what's a cluster? It's a connected component of open edges, so edges which have value 1. So if you draw your graph, you will see that some of these edges, open edges, form kind of clusters which are connected, and different clusters which are not connected if they are surrounded by closed edges. Kind of in the plane, everything is very clear. So one is interested in these properties of the clusters and how they are connected. For example, to gain information of the Ising model magnetization or some other models. Or you may be interested in these models as such, because they actually have a continuum parameter family of critical models, which is quite a nice thing. So I think this I already mentioned, maybe not much more. I said I'm going to focus on critical models. So I decided not to talk about criticality, because I'm assuming most of you are experts in it, and if you're not, you don't probably need to hear it in this talk. So there's just a particular choice of parameters, where the percolation parameter is related to the cluster weight in a certain way. So I'm going to have the square lattice, and the self-dual point is the critical point, which is a particular number. Never mind. For a range of Qs. So now here's the first question to the experts. So this Q belonging to the range 1 to 4, we know that we have a continuous phase transition by, I think, paper of Ugo, Vincentacion, and Vlada Sidorovicius, right? And we have positive association, which helps us a lot in the proof. But actually, also for the Q parameter between 0 and 1, strictly 1, there should be negative association, and there should also be a continuous phase transition. I'm not aware of a proof, or even if this statement is believed to be so. Hugo is saying no. Okay, so let's keep in this range. And actually, I'm excluding 4 most of the time, just because we got some explicit formulas, and I was too lazy to check what happens when Q goes to 4. So you need to subtract some divergences that come from gamma functions, but I think everything should be fine in the conjectures, because I'm making conjectures. It doesn't matter so much, you know, if the things are well defined. It's part of the conjecture.
So, sorry, do you need Q to be complex in your approach? Does it to be real, or can it be complex?
I think in the formulas, yeah. So okay, great question. So in this definition of the model, if you want the probability measure, maybe you want Q to be real, because, you know, otherwise you don't have a measure of mass 1. But you can find some formulas for crossing probabilities in these models, which are numbers between 0 and 1 with these parameters. If you take Q complex, okay, maybe you just analytically continue these values. So it depends what you look at. So in principle, in the end, maybe not. But then my question is, what does it represent? Does it answer your question? Maybe we can see later.
Yeah, maybe later, because for the moment Q is to some integer power, so for the moment
Yeah.
it can still be complex.
Yeah, that's true. But then this thing is a complex valid weight. So you get some complex measure. So it's not a probability measure, but you can define it. But let's start with this ranges of Q's and P's. And yeah, then let's see. Yeah. Any more questions at this point or comments? Maybe I forgot some. I didn't put any more names here because once again one should list so many names that it would probably take the whole day. So apologies for that. All right, so that's the model. So two parameters, P and Q. P is just a probability between 0 and 1. Or if you will, you can just think of it as a function of Q because I'm always going to look at the critical case. And then there's only one parameter, which is Q. And so far it's a positive parameter, or rather between 1 and 4. But, well, sometimes you can maybe take it complex if you wish. So let's see. It depends on the situation. All right, so here's now the picture a bit bigger. So I talk about stuff on the boundary, but I only defined a model on edges, on some finite graph. So here's supposed to be a finite graph, and there are these black kind of clusters. It's a bit small, but these are the open edges. I don't know if my open and closed are sometimes switched. Hope the terminology is consistent. So you can surround these clusters by loops. So here's this blue one, so there's some color. This is surrounding a cluster. It's going between two boundary points. You see the boundary piece here is belonging to the cluster, and so is over here. So we call this kind of boundary segments wired. And then in between, there are boundary segments which don't belong to any cluster, so they are called free. And you can put these loops surrounding all the clusters. There may be just cluster consisting of one point or bigger ones. And some of these paths are actually not loops, but they are some caudal curves which end on the boundary. And this is, of course, then going to be converging to SLE curves. While these loops, Wendelin was already talking about, they converge to CLE, conformal loop ensemble, that I will not talk about. So I will focus on this caudal curves between boundary points. And I'm going to fix the boundary points so that between some of them I have this kind of wired segment, and between some of them I have a free segment. So the starting points of these caudal interfaces will be fixed. They're called x1, x2, and so on for definiteness. Okay, and maybe we don't have to have a rectangle, but some kind of more general shape. Let's say we have a rectangular square lattice to be the simplest as possible, because I didn't want to focus on universality, but rather just trying to understand what's going on first in the simplest possible cases. All right, so then a nice observation that I wanted to point out is that in the critical case, you can actually rewrite the probability measure in terms of these loops. So there's this parameter Q to the 1/2 to the number of loops in the configuration. You need to do a calculation here, and there's the normalization factor will be not shown. And then a thing that I will show you soon. So this is coming from the boundary condition. So this theta omega, this is a random connection of these caudal interfaces. So in the picture, there are 3 caudal interfaces, red one, blue one, and yellow one. And there are 6 marked points. I don't know if you can see them, but they are between free and wired boundary arcs. So 1, 2, 3, 4, 5, 6. So 3 interfaces. And you see that they can connect in various ways. So this is one connection, that the blue one is going all across there. And then the yellow one has to be here and the red one over there. But they could also connect in some other way. So maybe this point here could be connected to, I don't know, over there. So that's a different connection pattern. And we will be interested in probabilities of different connection patterns in this model. This element of a matrix, which is indexed by connection patterns. So You can enumerate how many possibilities there are. So you just count all planar pairings. And the second index here is telling me the boundary condition, which is here called alternating. So I'm just alternating wired and free boundary segments. So I will tell you more specifically soon what's going on. But this is some number. This is also actually a power of q. So you can write the probability measure with this boundary condition, just in terms of the loops and something like that, which depends on this caudal interfaces. Okay. So that was the upshot. And I think I have more channel boundary condition here. So now a bit more clearly, I hope. So I'm going to denote the boundary condition, the wiring, by beta. So they are numerated by so-called link patterns or planar pairings. You don't need to worry about too much. There's an nth Catalan number of possible pairings. So for the 6 points, there are 5 pairings. They are shown here outside. So this blob here is supposed to be a wired piece. While in the middle here, I'm also wiring this arc together with that one externally. So that's a different boundary condition. Because now these two arcs, they are always in the same cluster. Okay? While that one is in its own cluster. Or maybe in the same one if there's an internal connection. And then there are a bunch of other options. So I'm just calling one of these options beta. Okay? And there's also a connection pattern inside, which was this random pattern of the caudal interfaces that we are interested in. So it's also taking values in the same space of these link patterns. And I'm going to denote it alpha. So then there's alpha and beta. Alpha is inside, beta is outside. And now this factor m that was in the previous slide is just the square root of q to the power of loops formed by this kind of boundary patterns. So maybe here you can see alpha is maybe underneath. So it's this 1, 2, 3, 4, 5, 6. And beta is in the upper half plane. So 1, 4, 2, 3, and 5, 6. Can count how many loops you form. And you take q to square root of q to the power of loops. And this is just adding to the loop term. If I go back, there. So here was also loops. So I'm just counting somehow boundary loops. Okay, so very simple, hope. So that boundary term is going to be denoted M because it's called the meander matrix. So that's why. So we are going to impose a bunch of boundary conditions labeled by beta. We are going to be interested in what's happening inside for the caudal interfaces. Okay. All right. So here's a motivation slide, which I added. Apologies, I was making slides in the airplane, so they're a bit messed up. So I hope you bear with me. So I just wanted to point out that critical models, including these random cluster models, are expected to become conformal invariant in the scaling limit, as you know, probably very well. There's a prediction for that. And I think there's rotation invariance actually proven, probably for this range of Qs by all these people, quite recently, by complicated arguments. So we are getting there. This approach I'm describing is more kind of naive in the sense that we just look at some particular observables, namely probabilities of crossings, and we try to show that they converge to something that we expect to in the scaling limit. So there's a bunch of work on the random cluster models. There are other models, but actually it's pretty hard to show this prediction or even make mathematical sense of it, you know, in general. So somehow it's usually very model specific. So we need some kind of exact solvability or discrete holomorphicity or some other kind of tricks to prove mathematical statements about conformal invariance. So there's only, you can count maybe with 2 hands the models that could be said that conformal invariance is proven, at least in some sense. So that's somehow a big obstacle for us. And maybe this program of trying to show first rotation invariance and then scale invariance, implemented by Ugo and others, maybe a good approach to try to get more robust results on this. So of course for the Ising model, that was one of the first examples where this was shown, starting by the work of Stas, Dima, Clément, Kostia, and so on. So the Ising model is kind of completely understood, I guess, at least the critical Ising model, and near criticality, as we heard, is much more difficult already. But yeah, there's a bunch of other models. And one feature, very concrete conformal invariance feature, is scaling limit of interface being conformal invariant, in the sense that if you take an interface, so this is a caudal curve, you take a scaling limit, you get a caudal curve, or more precisely, probability measure on caudal curves, living on, let's say, a simply connected domain with two marked points. If you move it by a conformal map, you move the marked point somewhere, the law of the curve will just be pushed forward by the conformal map. So that's a conformal invariance property. That is a feature of these SLE curves that were cooked up by Oded Schramm to describe these interfaces. And they have also this kind of domain Markov property that Wendelin also mentioned. And as in the case of conformal loop ensemble, also these caudal SLE curves are indexed by one parameter kappa and are uniquely determined by the two properties, conformal invariance and Markov property. And to prove this kind of convergence, there's a usual strategy. Maybe I will not go there, it's written there. I think many of you know already, and we don't really need it so much here. It's just I want to mention that the usual strategy, it's once again really relying on some specific things for each model, usually separately. So that's the big obstacle, that we cannot do general models at once. Okay. So here's the slide about SLE. So Schramm showed that if you expect conformal invariance and this kind of Markovian property, there's just a one parameter family of options for these caudal curves, which is called SLE kappa. And maybe more importantly for us, you can grow them in a dynamical way. So here in the Ising model simulation, I have from corner to corner, there's an interface which converges to SLE 3, kappa x3. By conformal invariance, I could just look at the upper half plane, which is there. I can start growing from 0, okay? And for any time t, let's say I pick some parameterization, I can stop growing and I just map outside of the curve back to the upper half plane by a conformal map, well chosen. And I keep track where the tip of the curve is mapping to. And that's a random point on the line, which is described by Brownian motion, with a speed which is this parameter kappa. So that's the dynamical description of the SLE curve for one caudal interface. And of course the conformal invariance kind of is in the Brownian scaling here. So if you do a scaling, nothing happens here. You can also translate, so you don't have to start from 0, but just for definiteness. So there's a concrete way to grow these SLE curves, and this is also how you explore. You start exploring, so this real line is a boundary of the upper half plane, and you start exploring by an SLE curve, and this is somehow how you do it in practice. So you run a Loewner evolution, so these conformal maps are called Loewner evolution, and you keep track of somehow this image of the tip, which is called the driving function, or driving process, if it's random. Okay, any questions so far? It's probably very familiar, so I hope. So then you can do more interfaces. And here I'm already starting to lack some references, probably. Let me just show. If you look at the caudal interfaces in the Ising model, so Wendelin was talking about loops, I'm talking about these caudal curves. You can show that all of them converge to some variance of the SLE, but now there's interaction between the curves, because there are more marked points and more curves, right? So just wrote NSLE, so capital N is the number of curves. So you can prove this in bunch of setups, actually with a bunch of techniques, but all of them need the discrete holomorphic observable that's already needed for the one curve case, and you can try to either generalize that to multi-curve case or do some kind of induction argument and kind of classification of these. I'm not going to go into that, but that can be done. Here are some names, and I'm probably lacking some names here. This is only for the caudal curves, so I left out all the CLE loops from my talk.
And what is this NSLE?
NSLE is a variant of SLE, where we have several marked points and we grow several curves. I think I will show a slide.
But that's not all. You should say something else, something more.
Yes, let me show a slide. Sorry. So this is one definition. I think it's maybe, it looks horrible, sorry. But let's look at the picture. So now we have more points, okay? Maybe we first of all say that we can grow the curves in any order, because somehow everything is very symmetric. So let's start from the first point. But then we need to keep track of what happens to the other points. So there are some spectator points which evolve as, so they're called capital V, t, so there's time. At each time instant I have the conform maps. And somewhere here is a stochastic differential equation for W, which is the driving process of this one curve, and these spectator points. And what you see from here is that you have a Brownian motion like before, plus a drift. And the drift has some form which has, we call it the partition function, but certain function of all these time evolutions, log derivative of that. And you need to understand that function in order to understand the NSLE. And these have been actually classified. So there are only certain functions that you can put here, basically because you want to be at least up to a stopping time. You want that this curve is absolutely continuous with respect to the usual one chord SLE. That's a reasonable assumption, right? And if you try to make a change of measure, you can use Girsanov transform or Radon-Nikodym theorem or whatever you want to call it to get this drift for the Brownian motion. But that comes from some martingale. And if you look at it, you will find a differential equation, for example, by calculating the stochastic differential of the martingale. Let's assume it's C2, that we don't a priori know. You find the equation which is over here. So I call it BBC equation from conformal field theory for those of you who know. If you don't, never mind, it's coming from stochastic calculus, okay? Then you try to find solutions of these. There's another condition which is just a conformal invariance property. Maybe let's not worry about it. It's fixing 3 degrees of freedom. But you have a bunch of system of equations, and then you can classify solutions to that. That's one way to say what NSLEs are. Then you need to find, which one you're looking at in the theorem. There's another way. Maybe I will actually show it here if I have a chalk. Here is the chalk, because it's kind of cute. So it's much more geometric. Let's say 6 points, 3 curves. So NSLE has 3 curves, gamma 1, gamma 2, gamma 3. And I'm imposing the following property. So it's living on this domain with these marked points fixed. Suppose I already sampled 2 of the curves, maybe this one and this one, and I decided they have to connect in this way. So these pair together and those pair together. So this corresponds to, in the discrete model, I condition on certain connection pattern, okay? So now what is this remaining guy? That's just the usual SLE, kappa, in this random domain, because it cannot cross the others if it's plausible from the discrete model. So you can show that if you look at probability measures on curves on this domain with these marked points, with a chosen pairing pattern, and impose the property that given n-1 of the curves, the remaining one is just the usual SLE in the random domain. bounded by the other curves. That measure is unique, and that's an NSLE. That's another, let's say, okay, kappa is maybe between, say, 0 and 4, just to avoid some stuff. It's a bit complicated to define, but I hope you got some idea. Yeah. But maybe this, so I'm gonna kind of be interested in the functions in the drift, so that's why I had this drift slide here. And this geometric part is kind of very nice otherwise.
In all cases, the connection is pre-chosen?
In that case, yeah.
In that, but can it also be random, like that the process
yes. So
decides it?
Yes. So if you do this picture, you can put here. So this is some system of linear partial differential equations. And believe it or not, you can actually find a certain number of solutions which are linearly independent. And the number is exactly the number of different pairings. Okay? So they form a basis in the set of all these possible partition functions, list modulo some technical bound. And you can take linear combinations, and that will give you a combination of different, where different connections are allowed. If you take a kind of, in a sense, symmetric one, they will actually come up soon. You will get this kind of unconditioned SLE. So that was in here.
You mean convex combination?
Yeah, so the partition function is defined up to normalization, because you have log derivative. Yeah, sorry, I'm cheating a lot. Yeah. So of course the probability measures are convex combinations, but they are given by, by these, I don't care about the normalization constant. Okay. Yeah. Yeah, thank you. Any more questions or comments? Also very happy to, if you point out if I'm cheating too much, I will fix the slides later. So yeah, so that's why I said there are various setups for this theorem. So this is a bit ambiguous because I didn't tell you. Either you can fix how they connect, and you can look at this kind of picture over there. Or you can say they can connect in any ways, and then you need this kind of SLE driven by Brownian motion with a drift. So in all these setups, it has been proven. So by Kostya, in the case where they can connect in any possible way. And then we have a paper with Vance and Bevara, who's somewhere here, and Hao, where we do this conditioned kind of version, which is on the blackboard there. But yeah, I didn't want to be too specific about this, but that can be done. It's kind of well understood. And depends on, what is your choice of NSLE, what kind of setup you're looking at. But the message is that everything is well understood. And there's a duplicate slide for the FK-Ising, maybe a little bit more different names. So it's the same kind of stuff. It's slightly more complicated because the curves are actually not simple. So if you know SLE with kappa bigger than 4 touches itself, it's not a simple curve anymore. And that's causing lots of technical difficulties for many of these proofs. But anyway, can be done. And you can do a very similar thing. Maybe a tiny comment for experts. So we have this Kara theory convergence of the domains. And as far as I know, there's actually an additional assumption discussed in a bunch of papers by Alex Karrila about what can happen near the marked points. I think maybe Dima and Kostya know more about this. So for safety, I'm putting it here because I think we need the extra assumption for the tightness. Okay, that's, I think, lacking in some of these papers of ours. So I wanted to point it out. I think there's an extra assumption which seems to be needed. But I'm happy to discuss if you have more knowledge about this. Okay. Anyway, so let's go to the crossings. So this slide you've seen already. So this was just how to implement more points and interaction. So we just get the drift for the for this driving process. And the drift has to satisfy some properties by basically conform invariance and by this property that it's coming from some martingale. And some kind of symmetry that you can grow them in any order. But yeah, if we look at the pictures about the discrete models, hopefully we believe that everything is somehow symmetric and very nice. So I don't need to explain it anymore, hope. Okay, so I said I'm interested in this partition function because that's related to the crossings, the properties of the crossings. Because if I put the particular one there, which is forcing a particular crossing, that's kind of the NSLE with a conditioned crossing pattern, like in the blackboard. While if I'm putting some linear combination, maybe modulo, there are some constants you can worry about, I can have different crossings with different probabilities. Okay, so here is now a result about crossings. This is already a little bit old, but let me mention it anyways because that was somehow one of the easiest cases to prove actually. So if you look at the spin-Ising model, which I haven't defined for you because I was hoping someone would before me, or maybe you already know it, you can look at the picture. So this is plus and minus spins with a certain Gibbs measure, critical. So I have this plus and minus alternating boundary segments. So remember I was talking about wired and free. So now this is slightly different. So this was supposed to be a side remark. So you can put also alternating plus and minus for the spin-Ising. You can look at what is the probability that these random chordal curves form a given connection. I call it alpha because I need some labels. Can look at the scaling limit and there's an expression. And the normalization you see is just sum over all of these possible options of the z. And the z is of course what's occurring in the drift. So the z is the same letter. So normalization is kind of, we don't care about it, it's just everyone, with the same constant. And so what we need to find out is the numerator. So what is this z? So that's giving the probability amplitude. And I'm just calling them pure partition functions. So they are exactly the ones in a specific basis of the set of partition functions, if you will. So there are some linearly independent functions which are in the solution space of this PD system, which is not a nice way to put it, but we cannot write them explicitly for the spin-Ising model. So this is somehow the best I can do. And in the later slides, I will show the problem which uniquely determines them. So let's wait for that because we have them for any kappa. So let's first look at what happens in different models and then I will show you more precisely what they are supposed to be. So there are some functions which we understand relatively well. We understand some properties of them, especially some properties that are predicted from conformal field theory, and they match with some properties of correlation functions of conformal field, which has degeneracy at level 2 for the Virasoro, so the phi 1, 2, which is notoriously well known, I guess. And of course there's a central charge depending on kappa. For the spin-Ising is the 1/2, like was already discussed. And you can do fusion, and you will find the fusion rules that you see in the CFT book. So somehow the message here is that even though we cannot write this guy explicitly, we can find a bunch of properties for it, which are what we expect from CFT. So that's kind of the nice thing. I guess it's the nicest we can do for the spin-Ising, at least at the moment, unless someone has found explicit formulas. I haven't. All right, so that's a kind of type of statement that we would want to prove. Look at the probability of connection in the scaling limit. Try to find some expression which is in particular conformal invariant. So you see here that the z is conformally covariant. I was hiding it a little bit, but there was some factors of the conformal maps coming to the front, but they cancel from numerator and denominator, so the ratio is conformally invariant. But we know more than that, so we don't only get conformal invariance, but we get a bunch of other properties. So that's the point why we would want to understand what the Z are. Okay. And yeah, if you're a physicist, you can say that it's a correlation function of these phi 1, 2 fields, which are the disorder operators sitting at these boundary points where the boundary condition is changing, like Cardy was predicting a long time ago. Okay, so that's one of the theorems. Then, because in the abstract I promised various things, I just put the slide about Bernoulli percolation here. I want to point out that here we can only do the side percolation on the triangular lattice because we need the convergence of the interface, which we still only have from Stas's proof 20 years ago for this case. So this doesn't quite fit to my random cluster model, which was Bonn percolation, but hopefully the limit should be the same. So here the normalization factor is just 1, otherwise it looks the same. There's kappa equals 6 for percolation. Yeah, guess I don't want to say much more about that, just that can be proven. Then there's the FK-Ising model, which was supposed to be the main topic. So once again, you see the same slide appearing again. Kappa changes a bit, and some names change a bit. So hopefully the message is getting through. However, here is a complication. So here is this, what I called meander matrix, which is this weight of the loops, because in general we can, in the random cluster models, and especially the FK-Ising model, which was the Q equals to 2 random cluster model, there was weight of loops that was coming from inside loops, and then another weight, which I called M, was coming from the boundary condition beta, which was outside, and the internal pattern alpha, which was inside. So somehow that's appearing over here. Do I need to go back to the slide where this was defined, or is it all right? Maybe raise your hand if you want to show the slide again. I don't see any hands. I don't know if it's a good or bad sign.
I remember the slide, but I didn't get what it meant because the because the inside and the outside.
It's kind of symmetric, right?
Yeah, but I don't know what you mean by the inside.
Okay, so I think I need to go back then. Yeah, let's do that. Yeah, I'm happy to have interaction. There.
Yeah,
So the point was that outside I put boundary conditions, which are these blobs outside the rectangle. And this is some kind of wiring of these boundary segments. So here is just independently wired. That one is wired, that one is wired, and that one is wired. Maybe, here was better. This is better, yeah.
You demand the same state.
Right, so this is just wired and free, and nothing else outside. Here was the internal loops and the boundary contribution. So this first picture is what was in the previous slide. I just thickened them so that you see this is paired together. But then I could also say that maybe this segment is wired with that one, so they belong to the same cluster. So there's an external wiring. Yeah. So that's outside, and that's called beta. And then inside is a random, maybe that's also. So inside is the random connection of the chordal interfaces, which are here are 3, red, blue, and yellow. And I don't care about the internal loops because they cancel in my formulas. So yeah, so that was the factor M. And you don't see it for the spin-Ising because there's no external wiring. It's just, plus and minus spins. You don't see it for Bernoulli percolation because everyone is independent. So yeah, but for random cluster models, you see this factor. And it's coming from the possibly complicated boundary conditions. Yeah. And so the theorem was about the probability of inside being given alpha.
And what was the denominator in that form?
Yeah, so I think I didn't say yet. Let's go back there. Yeah, so denominator, that's a complication as well. So there are two complications. Number one is this meander matrix, which is the loop term, which hopefully became slightly more clear. Number two is the denominator. So now it's not anymore just the sum of the z's, because somehow, again, because of this reason that there's this external wiring which is making things less symmetric. So if you remember Wendelin's talk, he was talking about this hookup probability, being the horizontal being 2/3 and the vertical being 1/3 or something, I forgot. Yeah, so it's not 1/2 and 1/2, it's something else. And that's the complication that you see here. So this one we can actually write explicitly, so I will show you something we can do. So I'm just calling it the partition function for the boundary condition beta. So you see it's decorated by beta. It's a normalization factor in a sense. And the numerator z is again the same kind of abstractly defined guy, unfortunately. And by the way, so this kind of formula, at least implicitly, it's in the physics literature, at least by Flores, Kleban, Simons, and Ziv. This is about 5 years ago, but maybe even earlier. Maybe Jesper, for example, have you seen this for ON models? You know, you must have seen this meander matrix coming up and all this stuff. So it may be obvious from earlier. So this is a reference I know of. I'm happy to get more references. So some of this was anticipated already. Maybe these formulas are nice, but they are also from Coulomb gas, so it's not super kind of surprising in a sense. Okay, so before showing the formula, let me say that I can vary kappa. It's exactly the same slide, just says random cluster model and kappa, because this is common for all kappa. But now this says conjecture, because we don't know how to prove it. And the only missing piece is the convergence of the interface. So difference here is a theorem, because we know how to prove convergence of the interface to SLE.
Sorry, so you're saying that what's missing is the convergence of a single interface?
And also for the single, but also for the one in a multiple interface. So so first I think the single interface convergence is missing unless there's some new result.
No, there isn't.
And after that you also need to, so actually it's quite complicated to get from one interface to several in here, so it's not trivial. So you need some complicated observable, or you need this kind of global SLE property that's on the blackboard that I think you know, with Vincent and Hao and me. So from one interface to many is also non-trivial, but the one interface is by far the most difficult. So once we have that, I think it's possible to somehow get to several. But yeah, I don't know. I don't think we have even one interface yet. And yeah, so that's the missing piece. So if you tell me that you can show convergence of interface, then I will change this to a theorem and add your name in it. Okay. All right. So let me show the formulas. I guess I don't want to run too much out of time. Let's see. So this was, so proof inputs. So maybe just mentioning why do we need the interface convergence? Because there's a SLE martingale argument, which is down here. So you follow the SLE interface, which is somehow exploring your thing. That gives you time evolution, and this ratio of these functions that I didn't show you yet, that will give you a martingale. You can use optional stopping theorem and induction to kind of carry out the proof. But you really need the first ingredient, which is the interface convergence. Okay, I think I will jump a bit. Sorry about that. Oops, okay. I wanted to show the formula. This one? Okay. So actually, you can reduce the complication from the boundary condition. So you can look at the alternating boundary condition first, and from that, you can actually get to general. There's a acute identity. I think I will first show what this denominator is, and then I will get to the acute identity, if that's okay. Yeah.
What is alternating beta then?
Alternating is just the one with no external wiring.
Ah, okay.
So,
Yes,
yeah. That's in the very first big picture. And that's somehow simpler because the meanders are simpler and everything is a bit nicer. Yeah. So I was planning to do it here, but I think I'll first show the formulas because it's more, I think more better in this way. So here's the F now. There's a lot in the slides, but hope you're not getting overwhelmed. I guess you will get the slides later. So this is a Coulomb gas integral. This was the denominator in the formula, which is telling you the boundary condition. So it's a Coulomb gas integral with the integration contour, which is to be determined, and that's very easy. It was already found by Julien Dubédat when he was trying to find the Z alphas, but unfortunately this wasn't the Z alpha, but this was the boundary condition, which we call F. So for example, if we have this, I don't know, connection, I'm just drawing in the half plane, x1 and so on, x2n. I just take n-dimensional integral, so as many integration as I have curves, and I integrate according to how this pairing is. So maybe I don't want to overlap, so just like that. So here is, I think my integration variables are w. So here is w1, that one is w2, w3. So some non-intersecting contours. And let's say kappa is big enough so that the integrals converge in the endpoints. If not, then you take some Pochhammer contours, but let's not worry about it too much. The point is that this integral is very simple. You just you integrate according to beta. So beta is this pairing of this integrand. Well, some of it is outside. This is very familiar from Coulomb gas, I hope. So that's explicit. And sometimes from this we can get the Z alphas. So that was the numerator in the crossing formula that I said was unfortunately not explicit. So the thing is that you can write this boundary kind of partition function for the boundary condition as a linear combination of the probability amplitudes. And here's this meander. So this is the probability amplitude. I think this should be alpha, sum over alphas. But now this matrix here, this meander matrix, is not always invertible. And in the most interesting models, it's not invertible. So we cannot solve for the z's using this identity. You can do it, for example, when kappa equals 8. This is the uniform spanning tree. That's kind of nice. And maybe in some other cases, also for some irrational kappa. But for FK-Ising model, for example, you cannot. So therefore, somehow, what's going on is that the probability amplitude Z, they are a basis in this big space of solutions to some PD boundary value problem, while this boundary condition partition functions, they are not linearly independent. So somehow, it's a little bit less nice than what we would want, maybe.
Does this have anything to do with logarithmic CFT?
In a sense, because if you take fusion of these functions, you will find logarithms. So it's very visible for the uniform spanning tree that I'm not talking about today. But there's an asymptotics that sometimes has a log correction. So in a sense, yeah. So how much time do I have left, actually?
2 minutes.
2 minutes. Okay, so in 1 minute the asymptotics, and then in 1 minute the acute identity I promised. So here's the asymptotics. So sometimes in the asymptotics, when kappa goes to 8, you see that these two so it's not so good. Anyway, there's a power law asymptotics, which gives you just the same kind of function with 2 points removed and with some factor. And if you do more of this, you may find that there's not a power law, but also some log correction. And you find somehow, you know, the other primaries that are supposed to be in the CFT by fusion. I don't know if it helps at all, your question, but this is where you may find logarithm. Okay, maybe we discuss later. And then I put the Qt identity and I stop there. And then I can show you more if you want privately. So this is just reducing general boundary condition beta to the alternating one, alt, by somehow comparing the two. And what's happening, this is the key. So remember that the probability measure was could be written, the weight could be written in terms of number of loops, square root q to the number of loops. So this is the internal loops and the boundary loops. And then the normalization factor. If you do some calculations using this meander matrix, this kind of pictures, and the random cluster model, you find that with boundary condition beta, the connection probability equals this horrible looking thing, but this is all about with alternating boundary condition. So this may be, I don't know if it's obvious to you, but we wrote it as a proposition because I haven't seen it. So that's kind of nice. So first what happened was that we proved convergence of interface for all boundary condition beta. Then we realized that actually you can reduce to the alternating case. But anyway, at least you have both results. So whatever. I should stop here. So thank you.
So we have time for one or two quick questions. Are there questions? Yes?
All of this is for the Bott model or the FK model.
Yeah.
But the Coulomb gas for the ON model looks very similar, except that you can extend the range of kappas.
Yeah.
And you could get similar boundary conditions where you change from wire to free just by saying that you want to insert a piece of curve from starting from that point.
That's true.
So, how much would change?
I think some of these formulas here should be fine because these are functions of kappa. And okay, I just put kappa between 4 and 8 so that the integral, this one would converge, but you can actually take kappa positive or maybe complex even. So here, yeah, q can be complex if you want in this formula because there's just a parameter. But then, yeah, so I guess what do we expect actually for the... So for the pots, of course, there should be connection to this. But for the ON?
So there, on the lattice, there are a few things that are a little bit subtle. I mean, you have some parity stuff in the pot model that you lose in the ON model. And so, when looking at something as fine as correlation functions, it's possible that that a few things could change. But I just wanted to know if you have thought about it.
So I haven't thought about it much yet, but I'm happy to also discuss. Because in principle, yeah, this is very kind of robust in the sense that this slide, for example, is kind of in continuum. So you can, if you know what kind of SLEs should be corresponding to your interfaces, then you can just work with the SLEs and forget about the lattice model if you don't know how to prove convergence. So for the ON model, yeah, we know what to expect. So maybe then there's the question if the meanders come in this way, because this was coming somehow from the loop weights, but it's also very similar. So yeah, I think one could do similar stuff, modulo convergence from the discrete to the continuum. At least I don't know how to do it, but maybe that will also people develop. Yeah.
And you never need the determinant of that meander matrix by any chance?
No, so I need it if I want to solve for this Z alpha from this formula. So if the determinant is non-zero, I can solve it, and then it's kind of nice. And if it's yeah, it doesn't. No, it doesn't enter here. So there's the other way of finding the Z alpha, which I didn't show.
Is it non-zero for typical or generic kappa?
For generic, yeah, for all irrational kappa. it appears that if you try to take a limit, so here's a proportionality factor which has some gamma functions. So for example, that will diverge or go to 0. There are some other things like that, but probably, yeah, so probably you could.
With respect to kappa in that formula.
Yeah, it seems so. But also this become actually linearly dependent. You see it for the critical percolation, where all of them equal 1. So, yeah, I mean, in principle, it's kind of explicit. So I said I'm presenting sort of integrability results or something like that in the abstract. So everything works for irrational kappa. So, yeah.
I think Jeffrey had a
Hi.
question.
You mentioned Stas's proof of conformal invariance for site percolation on the triangular lattice.
Right.
But you quite rightly, of course, made the remark that it doesn't tell you very much for your Bonn model. But it does tell you something rather similar for a Bonn model, but for a different Bonn model than the random cluster measure. Because, of course, you can turn site percolation into a Bonn model by looking at edges with like endpoints. And then the connections, of course, are the same. So there is a Bonn model on the triangular lattice for which you do get conformal invariance. And the dual of that in the Bond world is the hexagonal lattice, for which also you have a finite dependent Bonn model. Of course, your Bonn model is not finitely dependent, it's dependent through the existence of cycles, whereas these bonds are dependent through having a common n-vertex. So it's a different measure, but there is a Bonn model for which perhaps your techniques work.
I see. Thank you.
Other questions? Okay, so we have a coffee break until 4 o'clock. And thank you.
Thank you. I'll put this.